Okay, so the first thing I saw on the test a lot was people leaving the vector notation off of variables. Please get in the habit of just putting the arrow over the top. Or if you want to be different, you can do a squiggle on the bottom. Whoops, on the bottom, like that. I don't know, it sort of makes you look sophisticated. Either of those are fine, but it helps to clarify what your variables are if you use this, use these symbols. And then the related thing, so use vector symbols on vectors. A lot of people were just writing it as like F, A, B or whatever, but not putting the arrow over the top. And then a lot of people, and you might think like, oh, these two things average each other out. So a lot of people were using the vector symbol too often when you have something like this. People were writing like this, okay? So that vector symbol means that you have a quantity that can be broken up into components, okay? But the components themselves are scalars, okay? So use the vector symbol to represent the thing that has components, and then the components themselves, these are just numbers. Okay. Any questions about that? All right. Okay, so that's it for the test. The test overall was great. I mean, you made a mockery out of that test, so that's great. We're going to talk about two important things today. We're getting into statics of rigid bodies. Last time we talked about the table, how to use the table, and we'll see how helpful that can be when we get into rigid body statics. And we talked about moments. I guess the first thing, I'll start with this again. We already went through it, but the rotational equation of motion, or I call it rotational Newton's second law for statics, says add up all the moments on a body about some chosen about point A. They have to add up to be 0. And the statics just, the static part just keeps on giving. First it gave us this 0, which is nice. And now it also gives us the fact that this A can be anything. We don't have to be picky about what this A is. I'll call that the about point. So that about point is important. When you calculate the moment produced by a force, that moment is going to be different depending on the about point, except for one special case, one type of load that's different than other types. So the about point always affects the moment, except when you're talking about couples. And a couple is when you have equal and opposite forces acting at some distance from each other. acting some distance apart. And the surprising and unusual thing about a couple is when forces are organized in this way, they produce a moment that's independent of the about point. So no matter what you use as an about point, that couple applies sort of a pure moment with a certain value. And I'm going to do a derivation of what that is. It's not a long derivation, and I'm going to tell you right now, one of the questions on the next exam is going to be to go through this derivation, because I want this in your head, and to give one example of how to use it. So basically, this is a derivation of how to calculate the moment produced by a couple. But it also, the reason I think this is a nice thing to keep in your mind is it's a proof of why the about point doesn't matter. So here's a derivation of the moment produced by a couple. Okay, so let's say, so this is the object, okay? And let's say that we have a force F here. I'll say that this force, and it doesn't matter where our, what our coordinate system is. Let's say this is our coordinate system. And in this coordinate system, the coordinates of the location where this force F is applied is P1. Okay. And then at some distance, somewhere else at a point P2, you have another force vector. What does this force vector have to be if this is going to be a couple? Negative F1, or negative F, yep. The first thing to notice is, well, why don't I call this one F and this one negative F? Does that matter? It doesn't matter, except that you have to notice that what I'm doing here is pairing the point P1 with what I'm calling F. Okay, so if instead we call this one F and this negative F, we'd want to, for my formula that I'm coming up with to work out, you'd have to switch which one's P1 and P2. Okay, so what's the moment produced here? We need one more thing in order to calculate the moments produced by these forces. We need to choose an about point. I'm going to choose the about point A down there, okay? A is coordinates. So coordinates you can think of as a vector going from the origin to the point. So what's the sum of the moments produced by these two things? That's what we're trying to calculate. So the sum of the moments about A is equal to, well, what is the moment produced by F? You might want to, it's rho cross F, and that's right. And rho is going to be P1 minus A. I was just going to write this table. Pancake artist rho for marzipan. So we have P1 minus A. That's our rho vector. And then we're crossing that with the force vector F. So that's the moment produced by the force F. What's the moment produced by the force negative F? Yep. P2 minus A crossed with, now our force is negative F. What's your thinking on the, what is that, the distributive property of the cross product? Who thinks you can and who thinks you can't? You can. And you could figure it out if you wanted by going through the formula and, you know, with something in parentheses and seeing if it worked out. But you're just going to take my word for it. It's so much easier that way. So P1 cross F minus A cross F plus P2 crossed with negative F minus A crossed with negative F. And what's your thinking on the, this would be the associative property, right? Am I getting those backwards, or is that right? What about pulling these negatives out? Can I do that with a cross product? Yeah, you can. So we got P1 cross F minus A cross F minus P2 cross F plus A cross F. Okay, and this is the step where those where the dependence on the about point goes away. There's a negative A cross F here that cancels the positive A cross F. And now if you group these back together, you can rewrite this as P1 minus P2 crossed with F. Okay? So this couple has a total moment that has no dependence on the about point. Okay, so on exam 2, be able to derive this. You don't have to understand a single damn thing about this. You can just go through my steps. But it's more fun if you understand what's going on, you know. So be able to derive this and give an example of how it works. Bless you. Okay, so as an example, if you had an object like this, where this point is 0, 1, this point is the origin, and here you have a force going to the left of, let's say, 100 newtons. Here you have a force going to the right of 100 newtons. Okay, so how can I apply this formula to this? Well, you have to choose which one of these you're going to call F and which one you're going to call negative F. I guess I'll call this F. But, you know, keep in mind that's arbitrary. It just, for this formula, that just determines which one you're calling P1 and which one you're calling P2. So that means that the moment is equal to 0, 0 minus 0, 1 crossed with the force vector 100, 0. And so that is 0, negative 1 crossed with 100, 0. Which is, if you do it right, this is 3D, this would be 0, 0, positive 100 Newton meters. Okay, so does it make sense physically that that couple would produce a positive moment about Z? That's exactly right. That's the way to think about it. Yeah. So those two things would make it rotate counterclockwise. That's a positive moment, and that's what we got here. Okay. Yeah, so that's sort of the key thing about this. That's why couples are different than everything else. What we got through this derivation was A goes away. And so no matter what A is, you can calculate the moment this way, which means the moment produced by this couple is 100 Newton meters, no matter where your about point is. So it just doesn't even come into it. So I'll show you, so now I just want to show you how to put that in the table that we've been, like how that comes up in rigid body problems. So okay, so let me say one more thing about, this is kind of the bottom line. The bottom line is you can think of a couple as a pure moment. It's just a moment you apply to a body. Okay, and so when problems say that there's a couple applied here, they don't give it as two different forces. They give it as a moment. And that moment is the same no matter where the about point is, because we lost that dependence on the about point. Okay, so in the table, so you have the table pancake, artists, row, 4, marzipan. If you have a couple, then you don't care about any of those, and you just put in your couple M here. Okay, so this would be your couple. Okay. I think most of the time it's fine with me if you just write it this way, but you should keep in mind that it is a Z component. Yeah. Like the only reason I'm doing that in some examples right now is to just keep trying to remind you that it's really a Z component of a vector. But yeah, you could write it this way or 0, 0, M. Okay, so let's do an example. Fill out a table for a problem that has a couple and has some other forces in it. So let's say it's a circle. The origin is at the center. Let's say that there's a force F1 over here. I guess I gave a radius of 1 meter. there is a force F2 that's acting in a known direction where this angle is 30 degrees. And then here, there's a couple. In 2D, this is given as a little rotation. And let's say that it has a value of negative 450 Newton meters. And sometimes you'll see this written in a positive rotation direction as a negative 450, and sometimes you'll see it written clockwise as a positive 450. That means the same thing. So let's write the table for this object. Well, first let's put in the force F1. What's the location where that's applied? Yep, negative 1, 0. Oh, the about point, did I specify that? We could put that wherever we want. So let's put the about point here. Okay, so the about point then is 0, 1. To get rho, you subtract, p minus a, so that's negative 1, negative 1. The force vector is F1, x and y components. So negative F1y plus F1x. And now let's go to this force F2. Where's the point where that's applied? 1, 0, yep. So 1, 0. What about point should we choose for that one? Yeah, that's a trick question. I was trying to, that was entrapment. So in the same table, which represents the same free body diagram and stuff, you need to have the about point be the same all the way down. So once you've chosen that, every other load has the same about point. So this is 1, negative 1. The force vector, well, so, question? Okay, so this force vector is acting, so think of putting its tail at the origin of a coordinate system and figuring out the angle from here to here. So that's, this is also 30. So you can use 150 degrees. Or you can just use the fact that it's in the second quadrant and, you know this angle. But you're going to get negative 0.866 F2, positive 0.5 F2. Take the cross product, you get 1 times 0.5 F2 plus 0.866 F2. So let's see, what's 0.5 times 0.866 is 1.366 F2, I think. And then the last load we have is the couple. So none of this matters for the couple. We can just put this in as negative 450. And now the nice thing about this table is if this is a free body diagram, where do you get the forces for Newton's second law? You just go straight down this column, adding those up. Okay, and where do you get the couples, or where do you get the moments for the rotational equation? You just go straight down this column and add those up. So this plus this is equal to 0, that's Newton's second law, and this plus this is equal to 0, that's the rotational equation. Okay. Mm-hmm. Oh yeah, that should have been negative. Yep. I missed this negative here. So yeah, so this should be negative, so it should be negative 0.366. Is that right? Okay, so you're going to use these in Newton's second law and these in the rotational equation. And so Newton's second law then would be F1x, F1y plus negative 0.866 F2 0.5 F2 is equal to 0, 0. And the rotational equation says F1x minus F1y minus 0.366 F2 minus 450 is equal to 0, 0. And can we solve this? And how do you know whether we can or can't? Yep. So in 2D, this is always 3 equations, 3 useful equations. And so you just count up the variables. We have F1x, F1y, and F2. So we could solve this system of equations. Okay. Any questions about couples or putting these together in Newton's laws? Okay, so the next thing, and kind of the last thing that we have to do for rigid body statics is we need to talk about joints. Because if you look at this example, it seems like sort of a forced example, like, or sort of unsatisfying. Like, how do we know that this is a force vector F1, and how do we know this is F2 in this direction? In real problems, these are going to come into it in the form of joints, like connections between the body and the ground or the wall or another body. Okay, so now we need to talk about what the different types of joints are and what type of loads those different connections, those different joints apply to a body. Okay, and then we're ready to do pretty much any rigid body problem. So I'm going to talk about joints in 2D. Later, we'll talk about how to generalize these to 3D. So these are just attachments or contact points between different bodies. And each of these joint types is defined by the type of load that it transmits from one body to the other body. So it's defined by the load one body transmits to the other body. And so I'm going to sort of organize it into, I'm going to first talk about the joint types where you have a force with a known direction, and then I'm going to talk about joint types where you have force with an unknown direction, and then one where you have an unknown force with an unknown direction and an unknown couple. Okay, so it's just going to sort of go in that order. The first three, so the first three joints apply a force vector with a known direction to the chosen body. The first one of these is a pin sliding in a slot. So a pin and slot joint, it looks something like this. Okay, so here we have these two bodies. The one has the slot in it, and the other body is free to translate up and down when its pin slides up and down in that slot. Okay, can you picture what I'm drawing there? No matter which of these two bodies you're isolating, the force that's applied by that joint is perpendicular to the direction of the slot. So in a free body diagram, this would appear, so if you're isolating this body, there would be a force in that direction, okay? And if you're isolating this body, there would be a force, well, you could also, it doesn't matter which direction you choose. I guess I'll do it this way, just because we know by Newton's third law that these are going to be equal and opposite. But so when you see a pin in a slot joint, choose the body that you're going to isolate, and based on the angle of the slot, you know the direction of the force vector, and then associate it with a scalar variable. With this one, notice that the force can act in either direction. In either direction perpendicular to that slot. Right, like I could have drawn this arrow going the other way and it still would be perpendicular to that slot, and that would be fine. Mathematically, it doesn't matter because it's just determines whether you're going to get a positive or a negative answer for f. Either one works fine. Okay. Any questions about that? So the basic idea here is just that whenever we see any one of these joints that I'm describing, you replace the drawing of that joint with the load that I'm giving here. Then you go through Newton's laws to solve for what the magnitude is. Okay, the second type of joint that applies a force in a known direction is a frictionless contact. So if there's no friction, it's like a contact between the floor, a wall, or something. This is the one that you've had the most experience with. What's the direction of the force that's applied to this object by the floor? Yeah, it's perpendicular to the surface. So the free body diagram, if you're isolating this body, it's like this. You could call this whatever you want, but this is a case where it would be reasonable to call that N for a normal force. That's what a normal force is, just a force component that's perpendicular to the surface. If you're isolating the floor, you could treat it the same way. Notice that in this case, for this to make sense, the force direction should be away from the contacting surface. Okay, so if you draw this as your, so this is part of your free body diagram. Your normal force is going away from the contacting surface, and you get a value now that's negative. What does that tell you about this setup? So if you did this and calculated a negative value for n, it would mean that in order for this structure to be static, the ground would have to be pulling down on the object. And that just tells you that the way you're thinking of designing this thing is not going to work. You know, the ground isn't going to pull down on it. Whereas in the pin and slot joint, you don't have that. Like a negative is no problem. It just means the direction you arbitrarily chose was opposite of the direction the force applies. Here it does matter. Okay. And then the last one, where the force is an unknown magnitude in a known direction, is a roller joint. So that can be drawn a couple different ways. Sometimes you see it as just a like a disc or a cylinder with an object in contact with it like that. And sometimes you see it with the object coming in. Whoops. And wearing like a little roller skate, sort of. But those mean the same thing, okay? And mathematically, they're the same. In either case, that force is perpendicular to the contacting surface, perpendicular to the surface that you're rolling along. So the free body diagram looks like this. And again, it would be reasonable to give that the name N, because that force is normal to the surface. With a roller, again, notice that force should be away from the contacting surface. And again, if you get a negative value for that, that's a red flag about the system that you're thinking of setting up. Or if somebody came to you to ask why their system didn't work, that's why. So the force direction is away from the contacting surface. Okay. How many variables? So always what we're trying to do is come up with a system of equations that we can solve for a number of variables. How many variables are brought into a problem by any of these three joints? 60? No. So if you have a roller joint or a pin in a slot or a frictionless contact, how many variables does that bring up? Just one, that's right. Because the only variable is the scalar variable associated with that force, okay? So each of the above joint types brings one variable into the problem. So now we're going on to the types of joints that bring two variables into the problem. Those are the ones that introduce an unknown force vector. Like we don't know the magnitude and we don't know the direction. So the next two joint types introduce a fully unknown force vector to, you know, the problem or the free body diagram or whatever. Okay, so of all the joint types, this is the one that's going to come up the most often in this class, a pin joint. A pin joint is one where the motion, so the end that's connected to this pin joint, the end of this long bar, can't translate at all, you know, it's stuck there, but it can rotate. Okay, it's free to revolve around that. So free body diagram would look like, so there's the end of the object, and you just have a force, and you'd use the subscript notation here. And notice that this could be, so I have it drawn as a pin joint connecting this bar to the ground, but it could just as easily, and you know, in this class it'll happen a lot where this pin joint connects the bar to another bar, you know. That doesn't matter. It doesn't matter that that there's more degrees of freedom in this system because this one could wiggle or whatever. The only thing that you have to worry about at that pin joint is that if two members are connected by a pin joint, they apply a force vector to each other. And also, we'll see you can use Newton's third law then, because whatever force vector this one applies to this one is equal and opposite to the one this one applies to this one. And then the fifth joint type is contact with friction. We already talked about this one a little bit. You know, in this class, whenever you have contact with friction, you treat that as an unknown force vector. In this case, the free body diagram again would just look like this. If you want to get really picky with stuff like this, if you're trying to troubleshoot your problem, again here, you could, after you get an answer, you could go back and figure out some stuff about whether it makes sense based on whether the normal component of your force vector is required to pull the thing down to the ground. That can't happen. But it's a little trickier here than it was in the frictionless case. Okay, so each of joints 4 and 5 introduces 2 variables into your problem. And then the last joint is the supreme model. So number 6 is a fixed joint. Like if this beam is cantilevered from the wall, it can't, the end where it's connected can't translate along X, it can't translate along Y, and it can't rotate. And so the free body diagram represents this as an unknown force vector, F, and a couple, M. Okay. So this provides an unknown force vector and a couple. And so this brings 3 variables into the problem. Any questions about any of those? So those are the 6 types of joints that we're going to see over and over again in 2D problems. So one way to deal with this is, it's not that hard to memorize how to treat 6 different types of joints, and you could just memorize it. But the other way to think about it is to remember or notice that there's a variable introduced for every motion that's restricted by the joint. Okay, so let me write that down. So one way to remember these is a variable is introduced for each motion that's, maybe I'll say prevented. So let's just go through all those, well, maybe not all of them. Let's go through a few of those joints and just see sort of how that works. So like, for example, a pin joint. That pin joint keeps this member from translating in the X direction and keeps it from translating in the Y direction. And so you have 2 force variables that are whatever is required to keep those two, to keep it still in those two dimensions. But there's no couple applied here because this thing's free to rotate. A couple would be applied if rotation was also restricted, And so all of these, if you look at them, the pin and slot joint, the frictionless contact, the contact with friction, all of them up until the fixed joint, you can see that these two members are free to rotate relative to each other. The joint doesn't do anything to prevent rotation, and that's why there's no couple in any of those. But when you get to the fixed joint, that's the first time that not only is translation restricted between those, but the things can't rotate relative to each other anymore, and that's when the moment comes into it. So if you just think about what motions are prevented, that'll tell you what forces and couples are applied. Okay. Any questions about that? Okay. Let's take a break. Come back at 5 after, and then we'll go through some problems with this.